Welcome. Chapter 22C continues our discussion of respiratory physiology. We are discussing the transport of respiratory gases by the blood, beginning with oxygen transport. Molecular oxygen is carried by the blood in two ways. 1.5% is dissolved in the plasma. The other 98.5% is loosely bound to each iron atom of hemoglobin in the red blood cells. Each hemoglobin molecule is composed of 4 polypeptide chains, each with an iron-containing heme group, so each hemoglobin can transport 4 oxygen molecules. Oxyhemoglobin, or HbO2, is hemoglobin with oxygen attached. Reduced hemoglobin is hemoglobin that has released oxygen and is designated as HHB, as seen in this reaction. The loading and unloading of oxygen is facilitated by a change in shape of the hemoglobin. As oxygen binds, hemoglobin changes shape and increases its affinity for oxygen. As oxygen is released, hemoglobin changes its shape back, decreasing its affinity for oxygen. A fully saturated hemoglobin is one that has 4 oxygen molecules being carried by its 4 heme groups. Partially saturated is when the hemoglobin is only carrying 1 to 3 oxygen molecules on its heme. The rate of oxygen loading and unloading is regulated to ensure adequate oxygen delivery to tissue cells. Factors that influence hemoglobin saturation include the partial pressure of oxygen, temperature, blood pH, the partial pressure of carbon dioxide, and the concentration of the chemical BPG. The partial pressure of oxygen greatly influences oxygen's binding to and release from hemoglobin. The percent of hemoglobin saturation can be plotted against the partial pressure of oxygen. The graph is not linear, but is S-shaped and is referred to as the Oxygen-Hemoglobin Dissociation Curve. Please make sure to study this focus figure in your text. It describes the Oxygen-Hemoglobin Dissociation Curve. The amount of oxygen carried by hemoglobin depends on the amount of oxygen locally available. This ensures optimal oxygen pickup and delivery within our bodies. The bottom axis of this curve is the partial pressure, or the relative amount of oxygen gas dissociated in the fluid surrounding hemoglobin. So it increases as you move to the right, from 0 to 100 millimeters of mercury. The upright axis tells us how much oxygen is bound to the hemoglobin. At 100%, there are 4 bound oxygen molecules, as seen here. At 40 millimeters of mercury, the PO2 in the venous blood, the oxygen is 75% saturated. Notice that the shape of the curve is S-shape, and it is not a straight line due to the hemoglobin's binding properties. In arterial blood, the PO2 is 100 millimeters of mercury and contains 20 milliliters of oxygen per 100 milliliters of blood. So it's 20% of the blood's volume. The hemoglobin is 98% saturated. Increasing the PO2 due to deep breathing produced minimal increases in oxygen's binding. In venous blood, the PO2 is 40 millimeters of mercury and contains 15 volume percentage of oxygen. Hemoglobin is still 75% saturated. This change indicates the blood has delivered oxygen to tissues while in the capillaries. Because oxygen blood still has a PO2 of 40 millimeters of mercury, the blood still has a substantial amount of oxygen available to be used if needed. This is called the venous reserve. Taking a look at the oxygen-hemoglobin dissociation curve again, the top figure explains how hemoglobin in our lungs stays very saturated. In the lungs, at higher altitudes, where the partial pressure of oxygen is lower, 80 millimeters of mercury versus 100 millimeters of mercury, the hemoglobin saturation is less, but not by very much. So it only goes down from 98% saturated to 95% saturated. The graph is nearly flat in that area. So in our lungs, large changes in the PO2 cause only small changes in hemoglobin saturation. This quality is very useful for our bodies, as even in high altitudes or with lung disease, the hemoglobin in our lungs will remain saturated. Oppositely, in our tissues, a large change in PO2 results in a large change in hemoglobin saturation. Tissues have low PO2 because they consume PO2. Notice the curve is relatively steep at lower partial pressures of oxygen. So down at this end, it's very steep. In resting tissue, the PO2 is 40 millimeters of mercury and the hemoglobin is 75% saturated. In metabolically active tissues, like exercising tissues, the PO2 is even lower at 20 millimeters of mercury. Its hemoglobin is only 40% saturated, a drop of almost 35% saturation. This quality of hemoglobin ensures oxygen is delivered where it is most needed. When tissues need more oxygen, they receive more. In addition to the PO2, temperature also influences hemoglobin saturation. At increased temperatures, H+ ions, PCO2, and BPG can modify the structure of hemoglobin, resulting in a decrease in hemoglobin's affinity for oxygen. This occurs in the systemic capillaries and enhances oxygen's unloading, shifting the oxygen-hemoglobin curve to the right. I will show you what I mean by that in the next slide. Decreases in these factors shift the curve to the left, decreasing oxygen unloading from the blood. At this figure, we see the effect of temperature on the oxygen-hemoglobin dissociation curve. At a normal body temperature, 38 degrees Celsius, we see that at the light pink right here, we see a normal dissociation curve. At higher temperatures, like the 43 degrees Celsius, the curve moves to the right, which essentially lowers hemoglobin's affinity to oxygen. Let me say that again. At higher temperatures, like at 43 degrees Celsius, the curve moves to the right, which essentially lowers hemoglobin's affinity to oxygen. Alternatively, lower temperatures move the normal curve to the left, raising hemoglobin's affinity to oxygen. This curve shows the effect of PCO2 and blood pH on the oxygen-hemoglobin dissociation curve. The normal CO2 and pH curve is shown in light pink again, and is in the middle. At increased partial pressures of carbon dioxide and lower blood pH, the curve moves to the right, as seen with the bright magenta line. So we have, this is the normal, this is with increased carbon dioxide and increased H+ ions or more acidic. Lower partial pressures of carbon dioxide and higher than normal blood pHs shifts the curve to the left, as seen with the blue line right here. BPG is produced by red blood cells during glycolysis. BPG levels rise when oxygen levels are low. As cells metabolize glucose, they use up oxygen, causing increases in P carbon dioxide and H+ in the capillary blood. Declining blood pH or acidosis from the increased H+ and increasing PCO2 cause the hemoglobin-oxygen bond to weaken. This phenomenon is referred to as the Bohr effect, and it results in oxygen unloading where it is needed most. Heat production in active tissue directly and indirectly decreases hemoglobin's affinity to oxygen, which allows increased oxygen unloading in active tissues. So, in conclusion, increases in temperature, H+ ions, partial pressure of CO2, or BPG, shifts the curves to the right. That means these increases in temperature, H+ ions, CO2, or BPG, result in decreased affinity of hemoglobin to oxygen, so more oxygen is delivered. Hypoxia is the term used for inadequate oxygen delivery to tissues. It may result in cyanosis, or the tissue turning bluish-purple due to decreased hemoglobin saturation. There are several causes of hypoxia. Anemic hypoxia is from too few red blood cells or too little normal hemoglobin. Ischemic hypoxia is due to impaired circulation. Histotoxic hypoxia occurs when cells are unable to use oxygen because of metabolic poisons. Hypoxemic hypoxia is due to abnormal ventilation or pulmonary disease. And lastly, carbon monoxide poisoning also causes hypoxia because hemoglobin has a 200 times greater affinity to carbon monoxide than oxygen.